Hi students, this is A. Srinivas, lecturer in physics, Vignan Junior College, Vadlamudi. Students, in this session, we are discussing moving charges and magnetism chapter. Moving charges and magnetism is the very important chapter, especially in objective point of view. So in recent JEE main exams, that is in 2020 September JEE main exams, out of 25 questions, in some papers 2-3 questions are also given. That's why it is the most important chapter. Moreover, it is a creative chapter. Students must have good ability to apply the formulas, to understand the data and create a suitable equation. So it is a very important and nice chapter in subject point of view as well as examination point of view. So let us consider the contents that we have to discuss in the chapter. So in this session, students, we are going to discuss, first one is torque acts on current carrying coil in uniform magnetic field. In day-to-day life, we are using so many motors. So to lift the water, we need motor. To move a vehicle, it equipped with motor. To rotate a fan, it also has a rotating motor. So all rotating objects we use in day-to-day life must has this application. There is a current passing through the coil, which is kept in uniform magnetic field. Current carrying coil is kept in uniform magnetic field. It experiences a torque and it starts rotating. So this is a very good application for rotatory motion objects like fans, all motors. Torque is there. So torque acts on current carrying coil placed in uniform magnetic field. Next one is moving coil galvanometer. To calculate the current passing through the circuits as well as voltage difference across the elements of the circuit, we use the moving coil galvanometer. Next one, how to convert moving coil galvanometer to ammeter, which uses to find the current. Moving coil galvanometer to voltmeter, which is used to find the potential difference across the element of a circuit, and difference between ammeter and voltmeter. So these are the contents that we are going to discuss in this session. The first one, come to the first topic, that is torque experienced by a current loop. Especially here we are using rectangular loop in uniform magnetic field. So this torque experienced by current loop in uniform magnetic field has plenty of applications in our daily life. As I explained, especially we must use fan throughout the day in our daily life. The fans equipped with current carrying coil kept in uniform magnetic field, it experiences torque so that fan rotates. All motors also have the same principle, and this principle is also used to prepare moving coil galvanometer, followed by it converts to ammeter and voltmeter. So to derive the expression for torque experienced by current loop, which is in rectangular form in uniform magnetic field, let us consider a rectangular loop. Students, here you are observing a rectangular loop named by PQRS, rectangular loop. This is the axis at which this is pivoted. This coil in rectangular loop may rotate around this axis. Here PQRS is the rectangular coil. Here rectangular coil has length L. Rectangular means it has length and breadth. L is the length of the rectangular coil, B is the breadth of the rectangular coil. And B, here observing the horizontal arrow marks, long straight arrow marks, it shows the uniform magnetic field. Uniform magnetic field of magnetic induction B. Now we put a rectangular coil of length L and breadth B in uniform magnetic field of magnetic field induction B as shown in the diagram. Here see angle between the direction of magnetic field and the breadth is theta. Here we are indicating theta. This is the angle between the breadth of the coil and this uniform magnetic field. Here we have uniform magnetic field B bar. Angle between this B bar and breadth is theta. And here let us see. You may observe one more animation here. See, you observe the current now. See, this current is traveling. This is the coil. PQRS is the coil. It is a loop. Along this loop, it is made up of a metal wire and the current is traveling as shown in the diagram. That is in anti-clockwise direction. Current is passing through the coil. Let I be the strength of the current passing through the coil in anti-clockwise direction. This is the description of the coil carrying current I in uniform magnetic field. So once again, PQRS is the coil in rectangular shape having length L and breadth B. It is kept in uniform magnetic field of magnetic induction B, and angle between breadth and the magnetic field is theta. I is the current passing through the coil in anti-clockwise direction. Here then we have to consider the forces. Here, what is the force acting on the SP arm of the coil? Let us consider SP arm of the coil. Then what is the force acting? FSP. Then what is its direction? Here, to find the force acting on the current carrying wire in uniform magnetic field, we have the formula. Force acting on the current carrying wire in uniform magnetic field is F bar is equal to I into L bar cross B bar. This is the known formula, students. We derived this formula already in previous sessions. The force acting on the coil, force acting on current carrying wire of length L in uniform magnetic field B is F bar is equal to I into L bar cross B bar. In expanded form, in magnitude, that is ILB sin theta. The direction of force is given by Fleming left hand rule. So take your left hand, put the three fingers in mutually perpendicular directions, then thumb indicates F and this finger, forefinger, indicates B, middle finger, this one of our hand indicates current. Here when you apply this Fleming left hand rule to find the direction of force on the SP wire, SP is the a part of a wire of the coil. Here B is in this direction undoubtedly. See, B is along this direction. See the students, we indicated FBI are the terms indicated by the three fingers: force, magnetic field and current. So here B is along this direction, I is along this direction, B along this direction. I am comparing the given data, applying in my hand to find force value. This thumb indicates force and this is B and this is I. And I is in anti-clockwise direction in this sum. So I is in this direction, B is in this direction, then obviously F is in upward direction. That's why we indicated force acting on it one in upward direction. See, you observe the force direction. Here in this animation you observe the force acting on the SP arm of the current carrying wire in upward direction. And similarly on QR it is in downward direction obviously, because current direction has changed. Magnetic field is like this undoubtedly, but see, current is in the direction of QR. This is direction of current and this is the no change in the magnetic field. This is the direction of current, then force is in downward direction. Of course, these two forces are equal in magnitude. Force acting on the arm PS, force acting on the arm QR are equal in magnitude but opposite in direction. So they are acting along the axis, but one is in upward direction, another is in downward direction. They are equal in magnitude and they cancel each other. Net force due to these two becomes 0. Here now comes to the derivation part. So already I explained that force has the formula F is equal to I into L bar cross B bar, but here the length of SP is B, length of SP is the breadth of the rectangular coil, breadth of rectangular coil is denoted by B letter, then the expression for force acting on the current carrying wire is I into B bar cross B bar is the breadth and capital B bar is the magnetic field. I is the current passing through the wire. Then force acting on the arm SP, I into B bar cross B bar, expanding in magnitude form. So this is the expanded form, I small b capital B sin theta. If angle between, as shown in the diagram, angle between the breadth and the magnetic field is theta, then obviously we write the expanded form of cross product I small b capital B sin theta. Already I explained clearly about the direction in upward direction with this magnitude, direction is upwards. Next one, similarly QR comes to QR arm, lower arm of rectangular coil. I explained the force direction, downward direction by the Fleming left hand rule, and magnitude is I small b capital B sin theta, expanded form of this formula. So these two are equal and opposite direction, therefore these two cancels each other. Force acting on SP arm is an upward direction, QR arm is downward direction, they are equal in magnitude but opposite in direction, hence they cancels each other. Net force due to these two arms is 0. Now comes to the next one. Here next we have to recognize the force acting on the PQ arm, that is our aim. Next time is what is the force acting on PQ arm. Length is I and angle between this PQ and magnetic field is, this length and magnetic field is considered to be 90 degrees because PQ is in y direction and magnetic field is appears to be along x direction. In the diagram you are observing magnetic field is parallel to x axis, whereas PQ length of rectangular coil is in y direction, obviously angle between them becomes 90. To know the direction of force acting on the coil, of course the magnitude of the force is calculated by this formula ILB sin theta, that is okay, but direction of force is observed from the Fleming left hand rule. Take left hand, put the three fingers in mutually perpendicular direction. We know that this is F and this is B and this is I. So okay, here B is in this direction, B is in the, undoubtedly B, this middle, this forefinger indicates B, it is in direction. But what is about current? Current is travelling from P to Q in downward direction. So you rotate your hand such that this finger indicates the direction of current. So we have to rotate like this. So this is the direction of current, exactly equal to the PQ direction. This is the direction of current I, this is the direction of B, then this is the direction of force. FBI, same notation, FBI. I arrange my three fingers in the direction of BI, this is the direction of B, this is the direction of current in the wire PQ, therefore this is the direction of force. So I put dot here, it shows out of board. Out of board force is acting. So direction of force on PQ wire, PQ is the current carrying wire placed in magnetic field, then magnetic force acting on the current carrying wire is out of board. So see the direction. With the green arrow mark we represent it, FPQ is out of board. And similarly, what is about SR direction? SR. So RS, along RS length current is travelling from R to S in upward direction. So then in previous case we put the current direction downwards, now we have to put the current direction upwards like this. So this is the RS direction in which current is travelling, magnetic field retains in the same direction. Now current through the arm RS to the wire RS, current is travelling in upward direction, then the force is into the board. See the direction here, into. Once again see the animation clearly visible for you, into. So into the board the force is acting, so we indicate like that, FRS. So here FPQ is out of the board, FRS, force acting on the PQ wire is out of the board, force acting on RS wire is into the board. These are two equal and opposite forces. So let us find out the force value now. So far we discussed about the direction. Now comes to the force value. The force formula, always we are using only one equation. F bar is equal to I into L bar cross B bar. here length is L, B is magnetic field. We know that L is in y direction, B is along x direction. So angle obviously between them is 90 degrees. The expanded form is ILB sin 90. ILB sin 90. Sin 90 is 1. So it becomes ILB. I is the current passing through the PQ wire. L is the length of PQ wire. B is the magnetic field in which the wire is present. Then force acting on PQ wire is ILB along out of the board direction. I explained already about the direction. Along out of board direction, ILB force is acting on the PQ wire. Comes to SR wire. So same, consider the same formula, I into L bar cross B bar, and here on this wire also same condition, ILB sin 90, ILB, but it is acting into the board. So here students, the very important point is we consider PQRS as a rectangular loop carrying current I as shown in the diagram. This rectangular loop is kept in uniform magnetic field of magnetic induction B. Then we find out forces acting on four sides of rectangle. So on PS force is acting FSP, on QR force is acting FQR. These two are equal in magnitude, opposite in direction, they cancel each other. The resultant effect of this force is 0. These two forces is 0. Now comes to the vertical sides. On PQ, ILB force is acting, we calculated it out of the board. On RS, ILB force is acting, we calculated it, it is acting into the board. So on this rectangular, the two forces are acting, one is out of the board on PQ, RS into the board. These two forces of equal magnitude, opposite in direction, act at two different points on the rectangular loop, constitute a couple. It forms a couple, it acts like a couple and produces a torque and rotates the coil in about this axis of rotation in this direction. So PQ force is out of the board and RS force is into the board. These two are equal in opposite direction and rotate the coil in this direction about the axis of rotation. So it contributes a couple, it forms a couple, FPQ and FRS forms a couple and rotates the coil about the axis of rotation by producing a torque. Now we move on to find out the torque value. So far we calculated the force value and we concluded these two forces cancel each other. FPQ and FRS forces produces a couple and produces the torque. Now comes to the derivation of torque. Once again, I consider the same rectangle coil carrying current I, PQRS carrying current I, and this rose color line indicates the axis of rotation around which the coil is pivoted and it rotates. And here this is the uniform magnetic field. Next we have to find out the torque acting on the current carrying coil, that is our aim. We calculate the torque contributed. We concluded that the two equal and opposite forces are acting on the arms PQ and RS, and we have to find out the torque acting. Here angle between magnetic field and this side is theta. We know that already we indicate that angle in the data. The magnetic field B bar makes an angle theta with PS line. That means that is also angle made by magnetic field with face of the coil. Angle made by magnetic field with face of the coil is theta, which is also equal to angle between SP line and B bar, that is theta. Already we discussed about the couple acting. Here actually the force acting on PQ is out of the board. We calculated it out of the board. Number of times I explained, and force acting on RS arm is into the board. Into the board. This is out of the board and this is into the board, and it produces a torque. So if you assume this one is a rectangular lamina, PQ force and QR force, and it rotates in this direction. As these are rotating, perpendicular distance between the two forces goes on changing. Now, if you assume this is the coil, perpendicular distance is something, let it be some value. When the coil is rotating, the perpendicular distance is gradually reducing. So, that perpendicular distance is varying when coil is rotating about the axis of rotation. In present situation, theta is the angle between the direction of magnetic field and P. We indicate the out of the board value like this and into the board value like this. Then at this present situation, perpendicular distance between FPQ force, which is out of the board, FRS force, which is into the board, is Pn. Students, this is the important point. Perpendicular distance between out of the board force FPQ into the board force FRS. See the animation. FPQ, FRS. Out of the board and into the board forces. The perpendicular distance when coil is making theta angle, face of the coil is making theta angle with direction of magnetic field. Then perpendicular distance between these two forces, one is out of the board, one is into the board, is P. Clearly we observe this is a perpendicular distance in the right angle triangle. Pn is the perpendicular distance between these two forces, and to find the perpendicular distance consider cos theta. Here then by using cos theta we may calculate perpendicular distance. Then torque is equal to force into perpendicular distance. We know that torque is the product of when there is a couple acting on the coil, then torque is the product of magnitude of one force and perpendicular distance between the line of action of the forces. Once again I repeat, torque is the product of force and perpendicular distance between line of action of the forces. So FPQ and FRS are equal and opposite, so it contribute a couple. Then torque produced by the couple is the product of magnitude of one force and perpendicular distance between the two forces, that is Pn. And then here already we calculated, see students, we calculated the force is ILB, force is ILB. We calculated this force already in previous part of our discussion, ILB, where I is the current, L is the length of the PQ or RS wires, and B is the magnetic field. Now, when you consider cos theta, we have PNS right angle triangle. In PNS right angle triangle, consider cos theta. Cos theta is equal to Pn divided by adjacent by hypotenuse is B. On cross multiplying we get Pn is equal to B cos theta. Pn is equal to B cos theta. So we replace force by ILB formula, already derived and explained expression. Pn, now we calculated Pn is equal to B cos theta. Then torque is ILB into B cos theta, rearranging this equation. So ILB into capital B into cos theta. Here length into breadth. L is the length of the coil, we know L is the length of the coil, B is the breadth of the coil, then area of cross section of the coil, area of cross section of the coil is length into breadth. So tau is equal to, this is I, don't get confused, this is I. So this is the expression for torque, IAB cos theta. Students, we come to one idea here. We have a coil of area of cross section A, we have a coil of area of cross section A kept in uniform magnetic field of magnetic induction B. Current passing through the coil is I. A very important point is, very important point to discuss this formula, angle made by the magnetic field with plane of the coil is theta, angle between magnetic field and plane of the coil is theta. In that situation, in that consideration, torque is IAB cos theta. It may not be in cos form always. Under this condition, when we assume angle made by magnetic field with plane of the coil as shown in the diagram theta, then torque is IAB cos theta. I repeat, I is the current passing through the coil, A is the area of cross section of the coil, B is the magnetic field, angle between the face of the coil and magnetic field as shown in the diagram. Angle between face of the coil and magnetic field is theta, then IAB cos theta is the torque. Then we modify this formula. So, if there are n turns present in the coil, one turn may not be sufficient. If you consider a fan or a motor, it may have 1000 turns or 10,000 turns. So, a copper wire is wounded as a coil with so many number of turns. So, practically useful coils must have so many number of turns. So, according to practical situation, if this coil consisting of n number of turns, then torque increased by n times. So, NIAB cos theta, n are the number of turns. Now, remaining values are known for us, NIAB cos theta. Next one, here where n are the number of turns, here let us look into the diagram now. Now, we change the angle, NIAB cos theta is okay. When angle between magnetic field and face of the coil is theta, then NIAB cos theta, that is okay. But we change the data. Look, let's just look into the diagram, students. This is the line. Once again, look into the diagram. Look into the animation which is coming in the diagram. Here, this is normal. The line which I drawn now is normal. You may look into this is normal, n cap, normal, which is also direction of area of cross section of the coil. Area is a vector whose direction is perpendicular to the plane of the coil. If the magnetic field is making theta angle with the plane of the coil, then with normal it is making pi angle. With normal it is making pi angle. Makes theta angle with the face of the coil, then with normal it is making pi angle, which must be equal to 90 minus theta. Because the face normal perpendicular, normal to the face means it is perpendicular 90 degrees. As this is theta, remaining angle must be 90 minus theta. Therefore, here two terms, angle made by magnetic field with face of the coil is theta, then torque is NIAB cos theta. If you assume angle made by area vector, that is normal, area vector means normal line of the face of the coil with magnetic field, that obviously becomes 90 minus theta. So, here that angle is pi. Here if pi is the angle between normal to the coil and direction of magnetic field, then as I explained, this theta is equal to 90 minus pi, because this two sum of theta plus pi must be 90, theta is equal to 90 minus pi. So, replace theta is equal to 90 minus pi in the above equation. Here theta is 90 minus pi in the above equation, and it becomes tau is equal to n number of turns, NIAB cos of 90 minus theta replaced by 90 minus pi. We know that cos of 90 minus pi is sin pi. Then the expression for torque is NIAB sin pi. Don't get confused. Sir, why you are explaining two formulas in the same context, same torque? One you are giving NIAB cos theta, another words you are giving NIAB sin pi. What is the difference? At which context the above two formulas are applicable means, that's why I am clearly concluding the important point. So, the conclusion. Let us consider a coil having n number of turns. Let us consider a coil having n number of turns of area of cross section A, carrying current I, placed in uniform magnetic field of induction B, such that the direction of magnetic field with face of the coil is theta. If data is given in any problem or situation in which magnetic field is making theta angle with face of the coil, then torque is given by, we derived the expression for torque, NIAB cos theta, NIAB cos theta. In other words, if angle made by normal to the face of the coil, normal, this vector is the normal to the face of the coil, which is also area vector of the coil, not area of the coil. Area of the coil means it is a plane surface. Area vector means it is normal to the face of the coil. So, angle made by area vector or normal to the face of the coil with magnetic field is pi, then torque is NIAB sin pi. So, with respect to the angle, we write the suitable equation out of these two. If angle made by the magnetic field with face of the coil or area of the coil is theta, then NIAB cos theta. If angle made by magnetic field with normal of the coil is pi, then NIAB sin pi. So, remember. So, you may get confused. To avoid it, I explained it very clearly. So, remember this conclusion to apply the right formula for the right time to solve the numericals. So, students, we completed the first part of content in our discussion. So, we continue. So, one must be very careful in writing cos and sin. So, next discussion. Here finally, we may assume torque acting in the coil is NIAB sin pi, where pi is the angle between the normal to the face of the coil or area vector of the coil with magnetic field, then NIAB sin pi, or in vector form NIAB sin pi into n cap, of course n cap is the unit vector, then torque is Ni into A bar cross B bar. Students, in vector form Ni A bar, n cap is the unit vector along the area vector, n cap indicates area vector. So, A into n cap is area vector, let it be A bar. A into n cap is area vector. A is magnitude, n cap is the unit vector direction of area vector. So, A into n cap is area vector. So, Ni into A bar cross B bar. Here we write in magnetic moment form also, or M bar cross B bar. Students, here a current carrying coil, it may be a rectangular shape or a circular shape. I is the current passing through the coil as shown in the diagram. A is its area of cross section, I is the current passing through it, placed in a uniform magnetic field having n number of turns. Here the one important expression is NIA is generally considered to be M, magnetic moment. IA is the magnetic moment of one coil, IA of course magnetic moment of one turn. Magnetic moment of one turn is IA, magnetic moment of n turns is NIA. I is the current, A is the area of cross section. This current carrying coil is equivalent to bar magnet, students. It is equivalent to bar magnet. Already we discussed this part in the magnetic field produced by current carrying circular coil in uniform magnetic field. In the discussion of magnetic field produced by current carrying circular coil, we discussed this part. We know this result, we are applying it now. NIA is equivalent to magnetic moment. It is equivalent to bar magnet, whose magnetic moment is given by NIA for n turns, IA for 1 turn. Therefore, this NIA, I replace NIA by M bar vector. For n turns, NIA is magnetic moment. Therefore, tau bar is equal to M bar cross B bar, where M bar is magnetic moment of the coil, which is equal to NIA. So, here that is what we write. NIA is the magnetic moment of a dipole. This current carrying coil is equivalent to dipole like a permanent bar magnet. So, NIA is equal to M. The coil will rotate the anti-clockwise direction from OP, from top view according to the figure about the axis of the coil. Suppose if current is travelling like this, then the forces are acting out of the board and into the board as drawn respectively and rotates the coil. From top point of view, it appears to be rotating in anti-clockwise direction. So, if current is travelling in this direction, then it rotates in anti-clockwise direction. If current is traveling in opposite direction and it rotates in clockwise direction. This is the simple conclusion. Here some extensions to this formula. Tau is equal to NIAB sin pi. Suppose we have coil like this. If magnetic field is simply parallel to the face of the coil, magnetic field is simply parallel to the face of the coil, then the area vector, that is n cap, is making 90 degrees angle, then torque is maximum sin 90. Students, this is the conclusion for that formula. If B bar is the magnetic field which is parallel to the face of the coil such that the area vector or n cap is making 90 degrees angle with B bar, then torque is maximum. If magnetic field is, that is the conclusion here, if pi is equal to 90, then torque is maximum. Maximum torque is NIAB. To get maximum torque, condition is magnetic field is parallel to the area of the coil or magnetic field is perpendicular to the area vector normal. Parallel to the face of the coil means area vector is making 90 degrees, then torque is maximum. Unlike that, if magnetic field is perpendicular to the area of cross section, suppose perpendicular to the face of the coil and n cap and B bar are parallel to each other, then theta 0, then tau is equal to 0. Here then units of magnetic field, SI unit of course is Tesla, current is in ampere, then units of torque, we know that about the torque in mechanics, that is Newton meter is the unit of torque. So next we have to discuss the moving coil galvanometer. Students, I summarize the concept what we discussed so far. The first one is we consider a coil in uniform magnetic field and we found that on the length of the coil one force is out of the board, another one force is into the board and it contributes a couple and produces a torque and rotates the coil. The simple conclusion is, if the magnetic field is making some pi angle with area vector or normal to the face of the coil, one line conclusion, if magnetic field is making pi angle with normal to the coil or area vector, then torque acting on the coil is NIAB sin theta. So that is the main part of this discussion. NIA is equal to M, so MB sin theta. In vector form, tau bar is equal to M bar cross B bar. So next discussion in this part. So after a small break, we discuss the moving coil galvanometer. So students, next we discuss about moving coil galvanometer. So I explain the moving coil galvanometer in a video, then I derive in animation form also. So to have a clear idea about this moving coil galvanometer, let us see this video. In this video, we have a diagram of moving coil galvanometer. Moving coil galvanometer is a device which uses the function of the torque acting. The principle of moving coil galvanometer is when a current carrying coil is placed in uniform magnetic field, then it experiences a torque and coil rotates. This is the principle, and this can measures current up to 10 power minus 9 amperes. It is very sensitive device. It measures a very small currents passing through the wires, a very sensitive device to find even small currents by using this principle. The structure of the moving coil galvanometer is as explained in this video. So it has a coil. Students, see, look into this video. This is the coil made up of a metal like a copper, and with having so many number of turns. Of course, it is isolated between adjacent coils, laminated conducting wire, means there is no connection between adjacent wires. Current is passing through the coil. We have a coil made up of a good conductor like copper having n number of turns, first one, and placed in between two permanent magnets. So in the diagram we are observing red and blue colors. There are two permanent magnets. Between these two permanent magnets we put this coil, and this coil is connected to batteries plus and minus, and when current is passing through the coil in uniform magnetic field, we know that it should rotate. Here when magnetic field is parallel to the face of the coil, magnetic field is parallel to the face of the coil, then torque is maximum, because B bar and A bar makes 90 degrees angle, tau is equal to NIAB sin 90, maximum torque is acting. To get that maximum torque in the rotation of the coil, we use the concave shaped magnets and coil is present between them. And we provided a spring. When coil experiences a torque and rotating and needle is deflecting, spring opposes the rotation. When the torque produced by the magnetic field is equivalent to torque produced by the spring, it comes to equilibrium at some angle. By knowing that angle, we find the current. So that is the explanation. Let us consider once again, see this video. I explained with the help of this diagram. I continue this explanation with this video also. See here, this is the copper coil pivoted at a given point. About this point we fix the copper coil and it rotates about the pivoted point. And here on either side of the coil we use two magnets. Here on either side of the coil we are using the two magnets. See the students, on either side of the coil we are using the two magnets. These are permanent magnets, one having south pole, another having north pole, and here this is the spring provided for it, and we give connection to the coil by using batteries, positive and negative terminal of the battery. So when current is passing through the coil and current is passing through the coil, the current carrying coil now present in the magnetic field, then it starts rotating. So when this current is passing through the coil, see the student, it starts rotated. So torque acts, two equal and opposite forces acting on the coil, and it rotates, and we have some deflection here due to this rotation. So torque exerted by the magnetic field is NIAB, because we kept theta 90 degrees by using magnetic field parallel to the face of the coil. Torque is NIAB. We know the terms. N are the number of turns of the coil, I is the current in the circuit, A is the area of the coil, B is the strength of magnetic field, and needle deflects and comes to equilibrium and rests at some angle. Then the restoring torque, the spring opposes the rotation of the coil. We provided a spring inside the coil and it opposes the rotation of the coil. At equilibrium, the restoring torque is provided by the spring. If K is the torsional constant of the spring, pi is deflection, then restoring torque is K pi. At equilibrium, at equilibrium, so at equilibrium, the restoring torque acting the coil is K pi. K pi is the restoring torque. As the coil is rotating, spring opposing its rotation, which is provided inside the coil. At equilibrium, the restoring torque produced by the spring is equal to deflecting torque produced by the coil. Therefore, restoring torque is K pi, where pi is restoring torque is produced by K pi, and here we observe the restoring torque formula here. So restoring torque produced by K pi, the spring inside the coil opposes the rotation, produces restoring torque, that is K pi, is equal to deflecting torque NIAB. From this, here we calculate the I value. If K is known for the spring, pi is known, rotating angle, N is known, A is known, B is known, number of turns, area and magnetic field, obviously we find the current passing through the coil. So in this video we observe it. I explained the same phenomena in this animation also. Here these are leveling screws, the schematic diagram of moving coil galvanometer. Once again I am explaining in animation. LS are the leveling screws to keep the lower surface horizontal. As I explained earlier, I continue the same discussion in this animation. These are the two permanent magnets. Of course, they are concave shaped magnets to produce always radially producing magnetic field, so that B bar is always making 0 degrees, 90 degrees angle with the area vector. These are the two permanent magnets, north and south. See, this is north and this is south. And this is magnetic field always present from north to south direction B bar. And this is the torsion head there at the top. And here this is PW. PBW means phosphor branch wire, which retains its original position easily. And this is phosphor branch wire. And this is a coil. This is the coil. So see the coil once again, students. This is the coil kept in between two permanent magnets. Of course, to have a clear vision, I shown a video for a clear vision in which the magnets are concave shaped and coil is placed there. And this coil is suspended from the phosphor branch wire having some n number of turns. Already we named in the derivation PQRS. See students, PQRS is the coil name in which we made a derivation. Same name is that coil is kept here. Here this is a spring. In that video I shown a spring. Now we use the same spring here. Suppose due to the flow of current through the coil, if coil rotates, that is deflecting torque rotates the coil, that is opposed by the spring. Spring is suspended to the coil which opposes the deflection of the coil, and here we find out the deflection either by using the needle method or by using a mirror method. So this is the another method, that is the mirror provided here, and we are giving the battery connection. This is the one end of the coil, this is the other end of the coil. We give a battery connection to flow the current. Then current is traveling PQRS direction due to the connection of this coil with battery. So see arrow marks, students, there are so many changes you are observing in this diagram. Look into the diagram. When current key is closed, current is traveling, and so that the FPQ acts out of the board and FRS acts into the board, torque is acting and it rotates the coil. Of course, the magnets are concave shaped, so that always parallel to the face of the coil. B bar is always parallel to the face of the coil, such that B bar makes 90 degrees angle with normal. Always it is producing maximum torque, tau is equal to NIAB, and here it is the torque experienced in the coil is NIAB sin pi, and restoring torque in the coil NIAB sin pi, of course NIAB. And in this animation you may not observe the deflection of needle. In previous video I explained with the help of needle deflection. When the coil rotates and the needle provided for the coil deflects and makes some alpha or pi angle, then tau restoring torque produced by the spring developed inside the spring is K alpha. Then at equilibrium the coil rotates through certain angle alpha and comes to rest. Then because the restoring torque is balanced by, at equilibrium net torque is 0, restoring torque balanced by deflecting torque. This is the deflecting torque and this is the restoring torque. We assume, of course, sin pi, because of the special feature that we provided here. Here we make this sin pi sin 90 always by using magnet in special shape. We keep magnetic field parallel to the face of the coil for any position of rotation of the coil, such that sin 90 is 1. Here then At equilibrium we equate NIAB to the K alpha, where alpha is the deflection of the needle provided to the coil. Then NIAB, of course this is 1, is equal to K alpha. Then I is calculated by K by NIAB into alpha. So this is the purpose of the moving coil galvanometer. The purpose of moving coil galvanometer is to find the current passing through the coil to very small value. It is very sensitive device, measures even 10 power minus 9 ampere. The current ultimately calculated by this formula, K by NIAB into alpha, where K is the restoring constant of the spring provided here. Alpha is the deflection of the coil up to equilibrium position. N are the number of turns of the coil. A is area of cross section of the coil. B is the magnetic field produced by the permanent magnet. Then I is equal to K alpha by NIAB, of course. And already I put sin pi is 1 and we calculated I is equal to K by NIAB. So the radial magnetic field, what I explained here, by using radial magnetic field always we keep the sin pi is equal to 1, and this is the diagram given in academy book. In NCERT book we have this diagram, but you can't understood the derivation with the help of this diagram. That's why I explained with the help of one animation, before that with the help of one video. I gave a clear explanation for you. In textbook we have this diagram. You may not understood this diagram, explanation from this diagram. That's why I prefer the video as well as animation. In textbook we have this diagram. So the torque is with this formula. Ultimately this is the formula for us students. Current passing through the moving coil galvanometer coil is determined by the K alpha by NAB. As I explained, I is the strength of current through the coil, K is restoring constant of the spring used in moving coil galvanometer, alpha is the deflection at equilibrium, N are the number of turns of the rectangular coil, A is the area of cross section, B is the strength of magnetic field. Then I is, let it be G alpha, where G is galvanometer constant, the galvanometer constant equal to K by NAB. K by NAB is called galvanometer constant. Then I is equal to Z alpha. So by using a mirror method we may use, if mirror rotates by alpha, this angle is 2 alpha. If mirror rotates by alpha, in ray optics we have a concept. If reflecting mirror rotates by alpha, the image rotates by 2 alpha. From this we find alpha. But in NCERT book this method is not given. By the deflecting needle method we find the angle alpha. That was explained in the video. We use that method. There are two methods. I am giving two methods for you, but NCERT book method is the needle deflecting method. From that we calculate alpha and we find I value. Next comes to one important point. This is the important in objective point of view. Current sensitivity of galvanometer. So galvanometer now prepared by using this torque acting on the current carrying coil in uniform magnetic field principle. Anyhow it is finding current I. Then current sensitivity, it is the deflection of galvanometer per unit current. Deflection of galvanometer per unit current. So it is calculated by the formula alpha divided by I. If there is large deflection per unit current, then it shows a good deflection and it is more sensitive. The galvanometer becomes more sensitive while measuring current. It shows more deflection. More deflection for less current, it is more sensitive. That's why the sensitiveness is determined by the deflection per unit current. The sensitiveness of galvanometer is determined by the current per the deflection per unit current. Here alpha by I. From this formula alpha by I is equal to NAB by K. This is the expression for sensitivity of current sensitivity of moving coil galvanometer. Then voltage sensitivity, that is deflection per unit voltage. Very simple thing, deflection per unit voltage. So alpha by V. We know that V is equal to IR. Alpha by V. V is equal to IR. So alpha by I is known for us. That's why NAB by KR is the expression for current sensitivity and voltage sensitivity respectively. Okay, next one, our discussion is the very, very important discussion, conversion of moving coil galvanometer to ammeter. The ammeter means device which measures the current is ammeter. Device that measures the current is ammeter. Moving coil galvanometer converts to ammeter by connecting a small resistance in parallel to the moving coil galvanometer. This is the important point, students. A moving coil galvanometer converts to ammeter by connecting small resistance in parallel to the moving coil galvanometer. The small resistance connected in parallel also known as the shunt resistance. By connecting shunt resistance to the galvanometer, we increase the range of measuring the ammeter. So range of ammeter increases by connecting small resistance in parallel to the moving coil galvanometer. So galvanometer can be converted by connecting a small resistance known as the shunt resistance. Here, as I is the current measured by ammeter, Iz is the current measured by moving coil galvanometer. Maximum current that measures the galvanometer is Iz. We increases the strength to I. Maximum current measured by galvanometer is Iz. Iz is the maximum current at which galvanometer shows full deflection. Beyond that, no way of increasing the current because it shows full deflection for Iz. To increase the range of this moving coil galvanometer by converting it to ammeter, we connect a small resistance S in parallel to it so that the current measured by ammeter increases to I. Then if Iz is the current passing through the galvanometer, then current passing through shunt resistance is I minus Iz. By applying Kirchhoff's first law here, I is equal to Iz plus this current, Is. I is equal to, here we understood, I is equal to Iz plus Is by applying Kirchhoff's first law. Then Is is equal to I minus Iz, current passing through the shunt resistance. One more thing, a simple concept, as galvanometer and shunt resistance are parallel to each other. When two elements are parallel in current passing through them, potential difference must be same. So we equate Iz into Z is equal to I minus Iz into S. Potential difference across galvanometer is Iz. V is equal to IR, Ohm's law. So Iz into Z must be equal to I minus Iz into S. Or the S is equal to Iz into Z by just cross multiplying. We find S is equal to Iz into Z by I minus Iz. Of course, we rearrange this equation as S is equal to Z by I by Iz minus 1. So to increase the current strength from Iz in galvanometer to I in ammeter, Iz is the maximum current of galvanometer, I is the maximum current of ammeter, this whole equipment is ammeter. To increase the measuring strength from galvanometer reading Iz to ammeter reading I, we have to connect a small resistance in parallel to galvanometer. That small resistance is given by I by Iz minus 1. S is equal to Z by I by Iz minus 1 is the very important formula. So many times JEE main problems are given in this simple equation. Though it is simple, very important. Iz is the maximum deflection current in galvanometer. I is the maximum current measured by the ammeter. Then S is equal to parallel resistance connected is Z by I by Iz minus 1. Next, conversion of galvanometer into voltmeter. We convert moving coil galvanometer to voltmeter. Voltmeter is a device which measures potential difference, across a given element. So moving coil galvanometer is converted to voltmeter by connecting high resistance to the galvanometer. So G is the galvanometer having resistance capital G. Iz is the maximum deflecting current in it. We connected very high resistance are in series to moving coil galvanometer so that we may convert moving coil galvanometer to voltmeter. Then voltage measured by the moving coil galvanometer is equal to this total device is voltmeter now. This one is the galvanometer. When we connect high resistance in series, it becomes the voltmeter. So V is equal to total voltage measured by voltmeter is V is equal to voltage measured by galvanometer, voltage drop across galvanometer plus voltage drop across resistor. As these two are in series, same current is passing, then voltage is equal to Vz is equal to Iz into capital G plus Iz into capital R. This is the net voltage. If Iz is the current passing through the galvanometer, maximum deflecting current in galvanometer, then by connecting smaller resistance in series, the voltmeter measures voltage V, Iz into G plus R. As R increases, V increases. That's why we have to connect high resistance to measure more voltage. High resistance in series to measure more voltage in voltmeter. Vz is equal to Iz into G plus R. Or we write R value by the formula. When you modify this expression, we find R value as V minus Iz into capital G divided by Iz. So that is equal to V by Iz minus capital G. V by Iz minus capital G gives the resistance. So to convert a galvanometer which have maximum deflection current Iz to a voltmeter to measure maximum voltage V, the series resistor is given by R is equal to V by Iz minus G. So students, now I conclude the expressions for them. To convert a moving coil galvanometer which has the maximum deflecting current Iz to ammeter to measure I current, small resistance must be connected in series. The small resistance connected in series is G by I by Iz minus 1. To convert a moving coil galvanometer to voltmeter, high resistance R should be connected. The high resistance connected is V by Iz minus Z, where V is the voltage drop, voltage measured by the voltmeter. Now we see the differences between the ammeter and voltmeter. Very important derivation, very important explanation in board exams point of view. So ammeter, it is a low resistance instrument because we connected a small resistance in parallel, so effective resistance is very small. Ammeter is a low resistance device, voltmeter is high resistance instrument. The resistance of ammeter, already G is the galvanometer resistance, we connected a small resistance S in parallel, then effective resistance for parallel combination is R1 R2 by R1 plus R2, GS by G plus S. Already in voltmeter, G is the galvanometer, we connected a resistance R in series, so G plus R is the resistance of voltmeter. Here the shunt resistance is S is equal to G by I by Iz minus 1. So I write that S is equal to G by I by Iz minus 1, shunt resistance. And we calculated resistance in series V by Iz minus Z. Just now we derived them, just I am rearranging them in a table. So to convert a galvanometer into voltmeter, series resistor is high, that high value is V by Iz minus Z. Ammeter is the instrument used to measure the current in the circuit, so it must be connected in series. In series only same current is passing. So the current passing through the element also passes through the ammeter when it is connected in series, so that we measure the current properly. That's why ammeter must be connected in series. Voltmeter must be connected in parallel to the device, because parallel combinations have same potential difference. Parallel connected devices have same potential difference. So if you connect voltmeter in parallel to any element, that element and voltmeter have same voltage, so that voltmeter always connected in parallel to the given element to find the potential difference across that element. Resistance of ideal ammeter is 0. Here we assume a small resistance is connected in parallel to convert MCZ, moving coil galvanometer, to ammeter. Here that resistance of ideal ammeter is that small value is ideally becomes 0. Similarly, high resistance is connected in series to form voltmeter. That high resistance, if V increases, R increases, V increases. So ideally to measure any voltage, R should be infinity. Ideally to measure any voltage, R should be infinity. So resistance of ideal voltmeter is infinity. So here as effective resistance is Gs by G plus S. Parallel effective resistance is always less than the individual values. So its resistance is less than the resistance of galvanometer. Series gives always more resistance. G plus R always greater than G. So resistance is greater than that of voltmeter resistance. So finally the range of measuring current increases by using ammeter. Range of measuring voltage increases by using voltmeter. Students,